Now, let us also take note that we are going to talk about work, energy, and power for rotation. Ideally, we are supposed to consider all of these, but what we are simply going to state about the work is that when a torque causes an object to undergo rotation through a displacement theta, the rotational work done by torque is given as rotational work is equal to torque times displacement. This is how much rotational work is performed by a torque that causes a force that causes an object to rotate through some angular displacement. Then we are going to say something about the energy. Rotational work done is equal to change in the rotational kinetic energy of an object, where KER is the rotational kinetic energy. And it is given by KER is equal to half angular moment of inertia times angular velocity squared. We are defining this because it is simply similar to what we have seen before, similar to kinetic energy translational, which was equal to half mass times velocity squared. Where we had velocity squared, we have put angular velocity. Where we had mass, which was the inertia, we have put moment of inertia. So our class is going to end in the next 10 minutes. When it ends now, we can go to sleep and rest for the day. So we have seen rotational kinetic energy. Let us do a quick example to apply what we have just said here. Let us have a horizontal 800 Newton. Okay, a horizontal 800 Newton merry-go-round Let's consider a horizontal 800 Newton merry-go-round of radius 1.5 1.5 meters started from rest by a constant horizontal force, started from rest by a constant horizontal force of 50 newtons. Applied tangentially to the merry-go-round. To the merry-go-round. Then the question is, find the kinetic energy of the merry-go-round after 3 seconds. Find the kinetic energy of R of the merry-go-round after 3 seconds. After 3 seconds. So the example we are seeing here in short, we know that kinetic energy rotational is equal to 1 over 2 I omega squared. The question is, we need to find the omega squared. And what we are given is that we have omega initial is equal to 0, omega final is the unknown, and then we are also given that there is a time of 3 seconds to move from rest to final. And then what we also know here is that the angular acceleration can be gotten from final minus initial divided by time. But then whether we need this or not, we are going to find out if we need this or we don't. Then theta, of course, we also don't know. How do we find this? We can consider using omega final is equal to omega initial minus angular acceleration times time. So that omega final is equal to omega initial plus, this is plus this omega final minus omega initial divided by time multiplied by time, like that. Omega initial is 0 because it starts from rest. Omega initial is 0 because it starts from rest. Therefore, omega final now becomes, sorry, we are using a wrong equation, because this equation will not take us anywhere. What is on the right-hand side and what is on the left-hand side is the same thing. So let's not use this particular equation, because our interest is to find the omega final. We are also going to take note. Let's also look at the other things that are given in the question. We are also given that there is a force that causes the rotation, which is equal to 50 newtons. And we know that torque is equal to force times R. And we are given that R is equal to 1.5 meters. So instead of finding angular velocity using this, we can find torque is equal to I multiplied by alpha. So that alpha is equal to torque divided by I. And therefore we can have omega final is equal to omega initial plus angular acceleration times time. This is 0, so that our omega final is equal to torque divided by I multiplied by time. This is how we find omega final. And since the merry-go-round is a disk, we know I is half I R squared. So we can put what this is equal to. We will use what we already found here. We'll use this here. And we'll use the fact that I is equal to half M R squared. So we are going to put F times R multiplied by time divided by half M R squared. That is omega final. We can find M where M is equal to 800 newtons divided by G. M is equal to 800 newtons divided by G. So we can replace M by 800 newtons divided by G. This will give us the omega final. And finally, this is going to give us KE rotational is equal to half I omega squared, which will be equal to half multiplied by 1/2 MR squared multiplied by omega. We found it before here to be this. So we are going to lift this whole thing here and take it to the next page. FRT half MR squared. So we are going to multiply by FRT half MR squared. Here, this and this will cancel. We shall have half FRT as our kinetic energy rotational. So our class is about to end, and I'm just going to save the board so that I can share with us later on. And this is where we are going to end our class here now. You can put the F that is given, which is 50 newtons, R is 1.5 meters, and T is 3 seconds. So you can put these quantities here, half times 50 multiplied by 1.5 multiplied by 3 seconds. This is the kinetic energy.